Is that your computer?
Yeah.
Okay, cool. Awesome. Hello, everyone. How are you? I'm Brando. Yeah, we are organizing a talk, and we invited Kaiyu. Kaiyu is a postdoctoral researcher at Caltech in computing and mathematical science. He's working with Amika and then Kumar. Sorry if I pronounce it wrong. I'm sure most people know who she is. If not, she's like a great ML researcher. She works, I think, has been affiliated with Amazon. Kaiyu, the current speaker, received his PhD at Princeton, and where he was advised by Jia Deng, and has also worked with Olga Roosevelt and Dang Chen. We are today going to hear about LeanDojo, which is a method for interacting nicely with Lean, the Lean theorem prover, and also his model, the reprover, which uses, I believe, premise selection X very well, or something like that, right? But Kaiyu will tell you more about it. Let's give him a round of applause, and thank you for coming. Hope you find value in this.
Thank you, Brando, for the really nice introduction, and thanks everyone for coming. So I work on using machine learning for theorem proving, as Brando introduced, like in proof assistants such as Coq and Lean. And today I'm really excited to talk about our recent work in this direction, LeanDojo, theorem proving with retrieval-augmented language models. Just ensure everyone can see the screen, right? The screen is showing, okay. So automated reasoning is, as we know, an important task for formal mathematics and verified computer systems, including software, hardware, and cyber-physical systems. And because these applications have very high stakes, so we really want to formally verify their correctness and safety. And this is done using various tools for automated reasoning. They can be loosely divided into two camps by the level of human intervention required to prove theorems. On the right are SMT solvers such as Z3 and CVC5, and solver-aided programming languages such as Daphne and F-star, model checkers such as TLA+, and automated provers in first-order logic such as the eProver. These tools are automated in the sense that humans only write the specification, and ideally they just push a button and then the proofs should just come out. Although in practice, they may still require some level of human guidance. For example, in SMT solvers, you may have to manually enter some triggers to help the solver instantiate quantifiers. So despite they are not 100% automatic, they require only minimal human efforts during the proof search. However, these tools have limited expressiveness. Each of them is very good at solving a particular kind of problem, but it would be very difficult to, say, formalize undergrad or graduate level mathematics in first order logic. I mean, in principle, you could do that. You could formalize CFC set theory, but you wouldn't expect you can just throw any non-trivial math problem to a first order prover and it will just give you the results, because otherwise mathematicians can be put out of their jobs. The other camp of tools is interactive theorem prover or proof assistants. Examples include Coq, Isabelle, and Lean. F-star is somewhat in the middle because similar to Daphne, it has very strong proof automation based on SMT solvers, but it can also be used by humans as a proof assistant. So these tools are in general very expressive. Isabelle is based on higher order logic. Coq, Lean, and F-star are based on dependent type theories. And they have been successfully used in very large-scale formalization projects, such as the formal proof of the Kepler conjecture in Isabelle, as well as the verified compiler CompCert in Coq. This approach requires a lot of human labor to formalize the definition, formalize the theorems, and then to prove the theorems. As a result, these very large projects are multi-year efforts from very big research teams. This has become a major obstacle for formalized mathematics and verification to be more widely adopted. And to mitigate this problem, proof automation is critical. That is, we want to make the process of writing proofs more automatic and easier for humans. Note that here we focus on writing the proof, not formalizing the definition or formalizing the theorem. Although in practice, that part is also very label intensive. Here we show a simple example of proving a theorem in proof assistant. So starting from the theorem as the original goal, humans prove it by entering tactics. Each tactic transforms the goal, possibly decomposing it into sub-goals that are easier to solve. And this process is repeated until all goals are solved. So the formal method community has done a lot of great works to automate this process. There are efficient decision procedures for very specific domains, such as proving the equalities in rings. And people have also tried to outsource the proof obligations in proof assistance to external provers in first-order logic. So this kind of tools are called hammers, and they are widely used in Isabelle. Furthermore, there are generic search algorithms, such as best first search, that are implemented as tactics within the proof assistant. For example, the auto tactic in Coq and the ESOP tactic in Lean. In this work, we focus on machine learning, using machine learning to automate proof search. So we argue that machine learning is a very promising approach that is complementary to formal methods for proof automation. This is because machine learning, first, it offers the opportunity to learn from human written proofs. For example, in Lean, the proof assistant we focus on, there are about 100,000 proofs written by human that's just available on GitHub that everyone can use it as data. And for Coq and Isabelle, the number is even greater, although they are on the same order of magnitude. So that none of the formal methods, proof automation, can leverage this kind of existing proofs written by humans, and that's one unique opportunity provided by machine learning. And another opportunity is machine learning, especially large language models such as GPT-4. They seem to already learn a lot of mathematical knowledge from the large-scale pre-training on the entire internet. So here we are talking about mathematics, but the same reasoning more or less applies to formal verification. For example, GPT-4, it has performed exceptionally well in standard exams. Like in SAT Math, it has achieved the 89th percentile among human test takers. And another example is Google's Minerva model. So given this inequality, this is very simple inequality, it can produce this proof. So given, and LLMs, large language models, can also be useful for more advanced mathematics. Like in this June, Terence Tao, a Fields medalist, posted his experience interacting with GPT-4. And he believes models like GPT-4 can potentially be collaborators that offer suggestions to mathematicians. And a more recent study from Cambridge investigates how large language models can help us prove undergrad level mathematics. So given all these results, there are still controversies regarding whether the model truly understands mathematics or whether it just memorizes some correlation in the dataset. Or maybe what does it even mean to understand the mathematics? But putting aside all these philosophical debates, we still have reasons to believe that the mathematical knowledge in large language models can potentially be useful for guiding interactive theorem provers, such as Lean. So here is a list of existing work on large language models for theorem proving in proof assistance. So this area has been around for 1 or 2 years, and despite all these great works, I believe the area is facing a significant barrier. That is, none of the existing methods can be reproduced with a reasonable amount of effort. First, many of them rely on private datasets. here a check mark means the dataset is publicly available, and a cross mark means unavailable. And some data sets are partially available. For example, this paper from FIRST. Here, the dataset for fine-tuning the model is available, but their model is based on a pre-training model checkpoint that's internal to Google. So the pre-training dataset is not available. So that's the dataset. And second, none of this existing work have released the model checkpoint they trained, or their code base for training the model. And third, theorem proving requires a tool for the model to interact with the proof assistant, but only a handful of existing work has released this tool. And finally, the compute requirement in this prior work ranges from 1,000 GPU hours to 48,000 GPU hours, which is quite exclusive to industry labs with extensive resources. So it is a bit unfortunate that although this area has been around for a few years, there is surprisingly very, very little for the newcomers to build on. And I see this as one of the most important barriers in large language models for theorem proving. And in this work, we try to address this barrier. We introduce LeanDojo to address all these aspects. LeanDojo provides tools, data sets, and models that are completely open sourced. And also our model is very inexpensive. It needs only 1 week of training on a single GPU. So the goal of LeanDojo is basically to give researchers access to state-of-the-art large language model-based provers and with modest computational costs. So before we move on to dive into the details of LeanDojo, because we focus on Lean, so I'd like to briefly talk about the Lean proof assistant and why we choose Lean compared to other alternatives like Coq or Isabelle. So the Lean proof assistant is very similar to Coq. It is also based on dependent type theory, and in particular, a type theory called calculus of inductive constructions. Although there are some minor differences between Lean and Coq. For example, Lean has proof irrelevance, whereas Coq by default does not have proof irrelevance. And also, Lean has more liberal use of classical axioms, whereas Coq tends to be more constructive. So whether those differences are important really depends on who you are and what you want to work on. For the kind of work I do, machine learning for theorem proving work, those differences are not important at all. And also for mathematicians who want to formalize math in proof assistance, they usually don't care about those differences. But if for programming language researchers who want to develop, say, proof automation or algorithms for code extraction, or whether the logic is constructive or classic can make a big difference. So that's the type theoretic foundation for Lean. And the other difference with Coq is the ecosystem. So Lean has a strong ecosystem in mathematics. So it has a lot of formalized mathematics in Mathlib, which is Lean's centralized mathematical library. It includes a lot of very advanced mathematics, like grad level mathematics, such as algebraic geometry. However, the ecosystem is relatively lacking in formal verification. For example, in Coq, there are libraries for reasoning about floating point, but in Lean, we don't have such libraries. And what makes Lean appealing for machine learning is that Lean is not only a proof assistant, but also a general purpose programming language. Actually, Lean is very similar to Haskell, but with dependent types. The environments and local context, as well as the proof goals in Lean, they are not implemented in a meta language like OCaml, but they are implemented in Lean itself. and they're implemented as a hierarchy of state monads. So here on the screen, you see a hierarchy of state monad. On the left is the core monad. It provides you access to the environment. And the environment includes existing definitions, lemmas, existing theorems, etc. And then this monad goes through a monad transformer, which gives it another state, that is the local context. So here in the middle, in the meta monad, in addition to the environment, you have also access to the local context, like what local hypotheses are there and also what goals are there that you have to prove. And again, if you apply another monad transformer, you get the tactic monad. So tactic monad, in addition to everything we talked about, it also has access to the current goal. So this set of monads are all implemented within Lean itself. This is important for machine learning because it makes it really easy if we want to extract some data from Lean. You just write any Lean program that you just access the state of those monads, and then you can serialize this into a data set, and then you can train a machine learning model. We will talk about that in more detail later. And another perk of Lean that's important for machine learning is it has very strong support for metaprogramming. So you can write tactics directly in Lean, whereas in Cog, you need to write the tactic in another language. Either it's LTAC, like the DSL for writing tactics, or it's OCaml. But it's not nearly as convenient as in Lean. And also in Lean, you have access to the language's front end. So you can call the parser of Lean directly in Lean, which will turn out to be very important for us later. So that's why we choose Lean instead of Cog. And then in the rest of talk, I will dive into more details of the LeanDojo project. Our work focuses on Lean 4, which is the latest major version of Lean. And we begin by showing like an overall machine learning pipeline for theorem proving in any proof assistant. So basically, first you have Lean, and the first step is data extraction. You need to extract a data set from Lean. And then you use this data set to train the machine learning model. And after the model is trained, the model can prove theorems by interacting with Lean programmatically. And LeanDojo provides this entire pipeline. And I will first explain the tools for data extraction, and then to the tools for interacting with Lean, and finally to the specific model we trained. So great, let's start with data extraction. As we will see that data extraction in Lean is basically building a program analyzer for Lean. Although this may not be a very general program analyzer, it's very specific to the purpose we want, that is data extraction. So here on the right, you see a file in Lean. You have some definitions. Here's the definition of greatest common divisor. And then you have two theorems. Each theorem has a proof. So this is a raw code, but we want to analyze this code and extract our data set. So because first we extract the abstract syntax trees, ASTs, and also the tactics. As we mentioned, you can access Lean's parser within Lean. So it would be very easy to get the AST. And once you get the AST, it would be very easy to get the tactic, because you can just look at which nodes correspond to the tactics. So that's easy. But what's more difficult is how do you get the proof goals between those tactics? Because that's not directly visible in the source code, but it's very important for the machine learning model. It turns out the proof goals are available in a data structure called info tree in Lean. Here, info tree is actually for supporting the VS Code extension of Lean. Say this is a screenshot of using Lean in VS Code. On the right-hand side, you see a panel. In the panel, there are goals, current goals displaying in the panel. And for building this VS Code extension, Lean basically dump all the data into info tree. And then the VS Code extension can read this data. So if the VS Code extension can read this data, we can also read this data. So LeanDojo just gets the info tree and gets the proof goals from the info tree. And finally, we also want to extract premises. Premises are basically existing definitions and lemmas that you use in the current theorem. So in this figure, everything in color is a premise. And for each premise, for example, the GCD here, we want to record where it is used and where it is defined. And some premises are defined in the same file, but there are also premises that are imported from other files. So it turns out premises are the information we want about premises are also available in the info tree, because here in VS Code, if you put your mouse on a premise and you click right, and then you have this go to definition menu. So if you click on go to definition, it will jump to the definition of this premise. So that is to say the info tree, the data structure behind the VS Code also have this information inside. So then we also try to read this information from info tree and put them into our data set. So I'm going to run a simple demo for data extraction. I'm going to share the screen again once. Okay, are you able to see the Jupyter notebook?
Yes.
Is it large enough, or should I zoom in?
It's good, it seems.
Okay.
Thank you, Crystal.
Okay. Okay, so this is how we extract data from any Lean repo. So LeanDojo is a Python package. So assume you have already installed it. You just import from LeanDojo, import everything. And you can use LeanDojo to extract data from any Lean repo on GitHub, as long as it's public. But here for demonstration, we use this repo. We give it the URL and also the commit hash of a specific version of this repo. So you create a LeanGit repo here. Here, LeanGit repo actually is just it has only metadata. So because we haven't extracted the data yet. Then to extract the data, we call the trace function. So you call trace and you give it a repo, it will return a traced repo. So this step can take some time. So I'm going to skip this step, but I have already run it in the backend. So I'm going, after you have the traced repo has all the data you want. So you can query a lot of things. So first, in this repo, you have many files, and the files are DAG. They have dependencies. A file can import other files. So you can access the file dependency graph. And you can see there are more than 4,000 files here. And then say, say we want to go to a specific file. So we call traced repo, and we give it a file name. Then it gives us a traced file. So first we want to know in this, what premises are defined in this file. So we call get premise definitions. It gives you a list of premises in this file. Say if you look at the first one, it says it has a name, and you have the code in the file, and you have the starting position and the ending position, the row numbers and the column numbers. So that's a definition in the file. And then say I want to get the list of theorems in this file. You call this get traced theorems. You get 266 theorems. And then I care about a particular theorem with this name. So I gave it a theorem name. Then you get a particular traced theorem. And you can look at what theorem it is. You call show. So it will open the theorem here. So this is the theorem we are looking at. It has a theorem statement and it has two tactics. So let's go back. So you know the starting and ending position of this theorem, and you know when it was created. And you also know whether the theorem has a tactic proof. Here is true. And you can get the number of tactics in the theorem. Here is two tactics. And you can print the proof. So here is the proof of this theorem, two tactics. And then we can go to a particular tactic. So we call this get traced tactic. So the result has two tactics. So let's say we go to the second one. And this is a traced tactic. Here you have the tactic itself. It's a simplifier tactic. And you have the state before the tactic. So everything here is the state before the tactic. And you have the state after the tactic, because this is the final tactic. So after the tactics, it's no goes. So that's everything you can extract from this data set, and you can train machine learning models on those tactics. So I'm going back on to the slides. You can see the slides, right?
Yes.
Okay, so that's data extraction. And then we will talk about if we have a model, we have a machine learning model, say in Python, how can we use this model to interact with Lean? Because we cannot do it manually, we have to do it programmatically. So the key point is the tactic monad in Lean. So tactic M is tactic monad, and it can actually perform I/O to interact with the outside world. So here we see the monad hierarchy we have already seen. Tactic monad is here, it's the final monad. Actually, it also inherits some functions from the I/O monad. So in tactic monad, you can perform I/O. So then here is how we do it. So say you have this Lean file, you have a theorem here, and you want your model to interact with this theorem. So first, we replace the human written proof with a tactic that we write. It's called repo tactic. So then it becomes that. And because repo tactic can perform I/O, so we can wrap the repo tactic into a command line interface for interacting with Lean. And then once we have a command line interface, we can wrap it in any language, for example, in Python. So your model lives here in Python, and here is how it interacts with this theorem. Okay, we are also going to see a simple demo here. So you can see the screen, right?
Yes.
Here, say we want to interact with this theorem. So first we initialize it. It will give us a state 0. So we can look at state 0. So this is state 0. It's basically a proof goal. And we can print it. So now it looks nicer. And then, so this final line is the goal, and everything else is our hypothesis. Say we want to run a tactic, invert X on state 0, which gives us state 1. Let's print state 1. Okay, here is state 1. You see the X in the hypothesis, it has been reverted into the goal with a universal quantifier. And then say we want to run a invalid tactic, hello world, on state 0. It will return a Lean error, which says unknown tactic. So here state 2 is an invalid state. If you run anything on an invalid state, it will throw a runtime error. And you can run a sorry tactic, which is to give up the proof. So it will return a proof given up. And then let's try the tactic in the human written proof. So the first tactic is the ext tactic, which gives you state 3. And on state 3, you can try to run the simp tactic, which gives you a state 4. And here you see state 4 is a proof finished. So now you know the theorem has been successfully proved. So let me go back to the slides. Okay, you can see the slides, right? So that's how you have a model, how you want to interact with Lean. And then, so I will talk about the specific data set and specific model we trained in this, we collected and we trained in this work. So first we use LeanDojo to extract a data set that we call LeanDojo benchmark. It has about 100,000 theorems and proofs extracted from Mathlib. And among those proofs, it has about 200,000 tactics and about 130,000 premises. I want to emphasize that LeanDojo is not tied to Mathlib. You can actually use it to extract data from any repo or just your own repo, as long as it's on GitHub. And then having this data set, we train a model to prove theorems that we call Retrieval-Augmented language model. So here is the idea. So when you use the large language models to prove theorems, you are trying to generate the tactic from the proof goal. And existing methods, you basically have the proof state here. That's the goal you want to prove. And you train a transformer that gives you the tactic. So it's very simple. And the problem is the transformer, the model here, it has no knowledge of what premises are available, like what existing lemmas it can use. And it can still output premises, but the way it do that is it tries to memorize the name of the premises. So if this model has seen this name a lot in training, and then it can memorize it and use it in testing. But this is not very efficient and may not generalize if you have a very different project than the training data. So what we do is that given the state, the proof goal, we also consider the set of all accessible premises in the math library. So say here you have all premises, and in our data sets, it's about 33,000 on average. So first, you use this state as a query to retrieve relevant premises. And this is done by embedding the state and each premise into a vector. And then you can calculate their cosine similarity, and then you can retrieve the most similar ones. So here we have a few premises that are most similar. And then the retrieved premises are concatenated with the state and then used for generating the tactic. So in this way, the model can explicitly consider what premises are available and what premises might be useful, which hopefully can generalize better. And here are the experimental results. And the x-axis are two data sets, actually two random splits, two splits of the data sets. And the y-axis is the percentage of theorem you can prove. So higher is better. And you have 4 different colors. There are 4 different models. The gray one is our reproval model without retrieval. And the yellow one is our final model with retrieval. And the other 2 are baselines, like a tidy is a built-in tactic in Lean, and a GPT-4 baseline. So as a result, we see our model is much better than the baseline, and also adding the retrieval leads to a modest amount of improvement. And finally, after we train our model, we also try to use the model to discover new proofs in 2 data sets. One is MiniF2F, and the other is ProofNet. So in these 2 repos, many theorems do not come with proofs. So we try to see if our model can add more proof to their repo. And here are some examples of proofs discovered by our model. So that's the model. And here we have finished everything about LeanDojo in particular. And I want to emphasize that we have a website of everything open sourced in this project. And you're welcome to check it out. And also we are co-organizing a tutorial at NeurIPS this year on machine learning for theorem proving in proof assistance. And finally, I want to talk about some future work and fun applications. So here we use ChatGPT to prove theorems in Lean. So because LeanDojo gives you a tool for interacting with Lean, you can just wrap this interface as a plugin for ChatGPT. So let's look at it. So you tell ChatGPT what theorem I want to prove and where you can find the theorem. So it will call LeanDojo. It will give it the name and try to initialize the proof search. And LeanDojo tells it the proof goal. So ChatGPT tries to interpret the proof goal and lay out a high-level plan for proving this theorem. So this is just a very toy example. The theorem is just the addition is associative. And then ChatGPT runs a tactic and gets the results back from Lean. And it tries to interpret the results and run another tactic. Again, and then run the final tactic. So now LeanDojo says the theorem has been proved. So ChatGPT will know that. And I can ask ChatGPT to give me the final proof. So can you show me the final proof you find? So this is actually the proof found by ChatGPT. Although this is a very simple example, we actually tried more non-trivial theorems. I would say currently ChatGPT is not good at this task. It cannot prove non-trivial theorems. But I think in the future, there are more research to be done on how we can leverage these very, very large language models for theorem proving. Are there questions? No, I'll go forward. Okay. And finally, so far we've been talking about more like from a machine learning researcher perspective, like you train the model in Python and you evaluate the model on a lot of theorems. You look at how many theorems it can prove. But from the perspective of Lean users, they actually just don't care. What they care more is whether your large language models can give them a practical tool that they can use directly in Lean, and whether that tool can help them prove theorems. So here we have only one direction of this bridge, but we have also some ongoing projects trying to build the other direction, like how can we use AI to assist human users in Lean directly. So this is a work under submission done by undergrad students working with me. So here we use a large language model for generating tactic suggestions directly in Lean. Say we have a human user here, and they are trying to prove a theorem. They manually enter some tactics, 2 tactics here, and then they call this tactic called suggest tactics. So the suggest tactics will call our large language models under the hood, and it will display the suggestions here. So here, actually, the first suggestion can solve this goal, although this goal is very simple. And what happens under the hood is that we take the large language model and we convert it into a platform-independent format, the ONNX format. And then we can wrap it into a shared library. So after we have this shared library, we can use the following function interface in Lean to link to this library directly, so that the model is actually running locally on the user's desktop or laptop, and it actually doesn't require a GPU. And we take a lot of effort to make this package really easy to install. So any Lean user can basically add a dependency to their package, and it will automatically figure out the dependencies and try to download the model and then run everything locally. So that's for generating tactic suggestions. But that does not give you a proof unless the theorem can be solved by a single tactic. So in another work, we try to incorporate proof search into this large language model generated tactic suggestions. So here we develop a tool called LLM ESOP. So first, ESOP is a best first search implemented in Lean. Basically, the user can configure the rules used to expand the nodes in the search tree. So it's not completely a black box. It's actually a white box. However, the rules are configured before the proof search, but once the proof search begins, they are fixed. So for all nodes in the search tree, you apply the same set of rules. You do not consider the current proof goal. So it's independent of the proof goal. And so that's ESOP. What we do is we try to combine ESOP with the tactic suggestions generated by our model. So in that way, ESOP can apply different tactics depending on the goal. And we evaluate this tool on 50 theorems selected from a book called Mathematics in Lean. And we evaluate in two settings. One is the we call autonomous setting. That is, we apply this tool to the theorem without any human intervention. And the second setting is we use this tool to assist humans. So here, humans have to enter the tactics one by one. And after each tactic, they try to call this tool and see if this tool can solve the problem. So if they have to enter only a small number of tactics, then we know this tool is useful for them. And so here are the results. The first column is the average number of tactics humans have to enter. You see our tool require only one tactic, which is smaller than ESOP and other baselines. And the second column is the number of the percentage of theorems you can prove fully autonomously. So our tools can also prove more theorem in that setting. Cool. And finally, this work wouldn't be possible without a team of wonderful collaborators. And I'd like to thank all of you for coming to this talk. And I'm happy to take questions. Thank you.
Cool. So any questions? Yes.
I don't know, Kaiyu can hear me? Or
Can you hear us? I'm happy to repeat questions though.
I can hear you, but I cannot hear other people very well.
Sounds good. Just say it and I'll repeat.
Yeah, so I guess the question is, like how you said early on, that one of the problems with prior work on automated programming is that the compute costs are very high. And I was just curious how LeanDojo improved on that aspect.
Yeah, so the question, Kaiyu, is you mentioned earlier that the compute cost for Lean and doing proofs is high. So we're curious about in LeanDojo, what are the specific techniques, tactics? How do you make it more efficient in LeanDojo?
So there are multiple factors contributing to this. So first, if you compare the model size, our model is smaller than most of them, and smaller models usually are faster. We tried larger models, but it doesn't improve the results significantly, presumably because the dataset is not that large. And also, our model is built on publicly available model checkpoints. So we do not do pre-training, we do only fine-tuning. But some of the prior work, they also do pre-training. They pre-train on datasets that are specific to mathematics. So they cross on articles from arXiv and they pre-train the model on that. So that's another factor. And also, our model is trained using supervised learning only, whereas some prior work also has reinforcement learning. And that part is very, very expensive.
Awesome. So does that answer your question? Yeah? Cool. Awesome. Any other questions?
How did you run your experiments with GPT-4?
Yeah, so the question is, Kaiyu, how did you run your experiments with GPT-4?
Yeah, that's a good question. Let me go to a slide. So it's very similar to this one. So here you have it's a prior method. You have the goal and you use the model to use a fine-tuned model to generate the tactic. We just replace the fine-tuned model here with GPT-4. We just do like either 0 shot or 1 shot. For example, in 0 shot, we just tell GPT-4, so this is the goal I want to prove. Can you give me a number of tactics? And in the 1 shot setting, we also provide a few examples. Although in our experiments, we don't see a significant difference between these two.
Cool, awesome. Follow-up question.
Yeah, I wondered because a lot of paper, have shown that if you leverage GPT-4's API and if you supply with some vector store, I think similar to the RAG, what is using, they show significant better results.
Yeah, so I guess the question is that there's previous work that shows that you have vectoring, basically RAG, or retrieval-augmented ways to use GPT-4, you see significant improvement. So the question is, if you're using RAG, or how do you use RAG to improve your results, or how is it different to Reprover? Is that the question, more or less? No.
Yeah, I think one key thing is now you use embedding, right? You train a smaller model.
Yeah.
Right. Instead of doing that, what you can do is you can just use embedding and plus GPT-4's API, and that may give you good results.
Yeah, so I guess the question is, why don't you use the embeddings plus GPT-4's API?
I see. We haven't tried that. In this work, we have only tried this very basic method for using GPT-4. We do have some ongoing work trying to explore how like more sophisticated prompting with GPT-4, or also using premise retrieval with the embeddings. Currently, we don't have conclusive results yet, but I think it would be very impressive if you can make GPT-4 work as good as fine-tuned model. Because currently for this, for everything in this task, not limited to our work, we don't see, we're still trying to use fine-tuned model, and we don't see GPT-4 can beat fine-tuned model. So it's still an open question.
Cool, thank you for the question. More questions?
Yeah, this is technical, but why do other researchers not publish their models in code, and then what inspired you to publish it?
So question, why do other people not publish their code, and why did you do it?
I think there are a lot of reasons. One reason is this theorem proving pipeline is actually very complex. Like here, we only do supervised learning, but we still need data extraction and interacting with Lean. And if you want to add reinforcement learning, then you have some distributed infrastructure for the model to interact with the environment in parallel. You often, especially in industry, this kind of infrastructure is internal. So you will not base your work on open source libraries, but you will use your internal infrastructure, which makes your code essentially impossible to open source. And also, if your model is based on, say, if you work in Google and you base a model on Manova, then there's no way to open source. So that's one reason the pipeline is too complex. And also, I think there are some like personnel issues with this prior work, because most of them were done in industry. And then after some time, people just, because there are reorganizations in the industry, people just move on to other projects or to another company, and then just no one will open source.
Cool. And why did you open source it? Maybe that part of the question is cool to hear.
Because I guess, as mentioned in this slide, I see this, we don't have open source, we don't have fair comparison, we cannot reproduce existing results. It's actually the most important barrier in this area. Actually, at the beginning of this project, we tried to, the focus was to explore retrieval, to explore some like method side on this task. But as this project goes on, we find the real bottleneck is not we want a novel method. It's more like we need the infrastructure. So that's why we switch the focus to infrastructures. But by the end in the paper, we actually include both contributions.
Awesome. So for the sake of science, awesome. Any other questions? Scott has a question.
Hi, thanks for the talk. So I know that ESOP provides the user with the ability to add a weight, like a penalty to each premise that they provide. And that's what drives the best first search priority order. So I'm wondering if in LLM ESOP, whether you use that, maybe you use like a neural derived.
So this work is pretty recent. It's still ongoing. So currently in our code base, we are not doing that. We are using a fixed number for everything. But what I would imagine it's straightforward if I want to, because the LLM give you a confidence score for each generation. I can just use this confidence score as the score for ESOP, but we haven't done that yet.
I see. And in LLM ESOP, that's just a modified version of ESOP. It doesn't do anything else like call induction, for instance.
No, okay. It's a modification of ESOP.
Okay, cool. Thanks.
Awesome. So I'll get one question. So one of my questions from the chat is, I saw your plot where you have a big jump from GPT-4 to Reprover without augmentation. So the second one is actually from Reprover to augmentation. So obviously the source is sort of obvious. It's the retrieval that is making the second jump, but why is the GPT-4 to Reprover without augmentation happening? So the orange to the gray, what is the secret sauce there?
Because the gray one is a fine-tuned model and the orange one is just GPT-4. And it's not, because Lean is also a relatively new language. Maybe on the internet, on the training data of GPT-4, there is not that a lot of data on Lean. And also because there's a mix between Lean 3 and Lean 4, I think GPT-4 tends to struggle with that. So it will, sometimes it outputs a mix of Lean 3 and Lean 4.
Cool, awesome. And quick question, what is the base model for Reprover?
It's a by T5. So it's a modification of T5 that operates directly on bytes. So you don't have tokenization. You just have a stream of bytes and you map it to the output string of bytes.
Awesome. Any more questions, guys? No? Yeah? Cool. Okay, last question for Brando. He has it on the chat. So when you say the size of Baldur, is it 62 billion or is that a typo? Because you wrote, it wasn't clear why you would write it the way it was written.
They have a range of model size. The largest one is, I believe, is 62 billion.
Okay.
They also have 7 billion or other sizes.
Excellent. That was it. Cool. Well, thank you so much for coming, Kaiyu. Yeah, let's give him a round of applause. Woo!
Thank you for inviting me and for the introduction and for everything.
No worries. Thank you for sharing your knowledge and making it open source to everyone to build on science. Great. Thank you.
Thank you. Hope to see you at NeurIPS.
Yeah, for sure. Let's meet.
Bye.
Bye.
Anyone mind going to the Berkeley Lean Talk today?